So now what we're going to do is we're going to derive the famous kinematics equations from calculus real quick. It's because I don't want to just tell them to you. I want to show you, where they come from. And then the second half of the day, we're going to do problems. So we are going to do problems. But first, let's just see where they come from, because I want you to understand this is motion with constant acceleration. So the kinematics equations you learned and memorized in high school physics, if you took it, are just for constant acceleration. Okay? Acceleration changes, those don't apply anymore. You have to do calculus to get the new ones. But these are very useful because they're only for constant acceleration. Well, what about uniform motion? Well, that's constant acceleration. That's acceleration equals 0. So you can use these equations and just put a equals 0, and then you can use them for uniform motion. So they're really useful for everything. So what we do is we start with this. We say a equals dv dt. That's where it all starts, right? We have position, velocity, acceleration. We're going to start at acceleration and integrate our way back up. Okay? So write all this down. This is good knowledge to have. You don't have to be able to do this derivation on your own, right? That's not why I'm showing it to you. I don't want you to be able to memorize it and do it. I just want you to see where it comes from. So we say, so from 0 to t, what are we going to get? Okay, well we say, okay, then it must be, I have this, and I'm trying to find delta v. I got to integrate both sides, right? I'm going to bring this dt over here and integrate. And what that's going to tell me is vf minus vi. See, it was the velocity integral gives you the position. So you go up a level, right? We go up a level from acceleration. It's vf minus vi equals the integral, the sum of the acceleration times dt. In this case, it's constant. It's not even going to vary. Okay? And we're going to integrate from 0 to time t. Okay? If you're a mathematical purist, yes, one of these should have a prime on it. We're going to leave it off. It'll be okay. If you have no idea what I just said, don't worry about it. We're going to integrate from 0 to t. Okay? Okay, so let's do that. So vf minus vi. What is the integral of a constant? It's just the constant times the variable you're integrating with. Right? So the integral of a is just at. The integral of a with respect to time is just at from 0 to t. So the way, if you haven't had calculus, the way you handle the limits is you would plug in this one minus plug in that one. Right? So you get vf minus vi equals at minus nothing. Equals at. Right? Which is what I wrote down somewhere else already. Right? So vf minus vi equals at. We got it just from this, and it worked because a is constant. Right? Here we got it from the integral. A is constant. It's going to give you the same answer. If a weren't constant, then we would have got a different answer. But a is constant, so that works. So there's one of your fundamental kinematics equations. How does velocity change when you accelerate? V final equals V initial plus at. Okay, so now we know how the velocity is going to change. So now we're just going to do it again. Let's just keep it going. We know that v equals dx dt. All right, and we say, oh, how does it work? Let's see. We're going to take the integral of v. So that tells us xa minus xb. So from that same 0 to t, from the origin of time to some time, we'd say x final minus x initial, there's the change, equals the integral from 0 to t. And now we're going to put in v. But we can't just write v because it's not constant. Right here we just wrote a because a is constant. That's easy. Now v is changing. Oh no, v is changing. So we put it in here and we say v after some time is v naught or v initial plus at. So we say v initial plus at. So now we put in a function for v. See that? With a dt on here. Like that. We put in a function because it is a function. Let's see. Right. Okay, so then what do we do? Well, we do our integral. We say xf, x final, I can't see that, x final minus x initial equals what? Okay, if you got to integrate something with two terms, you just do each term individually, right? So vi is a constant. The integral of vi with respect to t, a constant is just vi times t, right? Vi initial times t. That's starting to sound familiar. And the integral of something to t goes to t squared, and you divide by the 2. Plus 1/2 at squared. Right? Evaluated from 0 to t. Okay. So now what I'm going to do is I'm going to write x final, and I'm going to go ahead and bring the x initial over here, equals x initial, and now we're going to evaluate this side, and you see when we plug in t, it's just the same. When we plug in 0, it's just 0. So this minus a 0 is just this. So I'm really just going to write this again. xf is xi plus v initial t plus 1/2 at squared. Right? And that's your other kinematics equation. All right, like that. This is the one, maybe that sounds familiar. Vixi, vit plus 1/2 at squared. Right? This is what you use when you're solving constant acceleration kinematics problems. Okay. Yeah, so this is basically when you're solving a problem where an object ends up, because we'll come up with another equation later, after, I want to stress, constant acceleration for time t. So really you only need 3 equations in kinematics, right? You need this one and this one, and then it's good to, well no, actually you only need these 2. Because you can say, what about uniform motion? For uniform motion, make a equals 0. And what is this? X final equals x initial plus vt. It's the same equation. This is d equals vt right here. Final minus initial is d vt. If you just make the acceleration 0. So this is really everything right here. There's one other one that I'll tell you about in a little bit that we have to derive, but it's really just a combination of those. Okay? So they aren't mysterious equations that came down on a stone tablet or whatever. They're really just derived straight from calculus. And this is why I say you have to have calculus-based physics. You can't really do non-calculus-based physics. It's not possible. Okay, I'll figure out why my phone isn't beeping at me here later. Why did they use to write 1s like an integral? They didn't write 1s like an integral. We write an integral like they used to write 1s. They had it first. The politicians had it first. How should I be worried if these derivatives aren't making sense to me? No. Well, no, not today. Yeah. No, so we will not make you do a derivation like this. Eventually, you'll be good enough to do a teeny bit of calculus on an exam. We'll show you the tricks. Okay, I haven't had time to go over the tricks yet, but we'll either go over them in class or I'll make a little one-sheet reminder. Because we just need to do the most basic integrals. T, t squared, sine, and cosine. That's really it.
So for these equations, is when we have the like the line from the 0 to t, like vf minus vi is at from 0 to t.
Yeah.
You always plug in t for a.
Oh yeah. So I'm sorry. So this is the thing where I didn't vary my notation, right? You're plugging in this t for this t.
Okay.
Yeah. You're plugging in t for t and then minus plug in 0 for t.
Okay.
Usually you have 2 different letters there, but this time we don't. Yeah.
That first step when you come from a equals to vt to vf minus vt.
I was just sort of following this rule. I guess what I should have said is the rule is that v is dx dt. If that's true, then this is true. So we're not kind of going through it algebraically. We're just applying the
Very first step.
here. This is the definition of acceleration.
How do you get to the next?
The fundamental theorem of calculus. Anytime this is true, then this is true. You say this minus this equals integral of this times this. I'm not going to justify that, yeah, but it's called the fundamental theorem of calculus. Okay, let's see.